We're talking about the quantum mechanical model of an atom. This is lecture 3.3. Last time we dealt with the Bohr model atom and the idea that an atom was of a particle nature. So say we have an atom that's a particle here. The quantum mechanical model of an atom suggests that particle also has wave functions or wave characteristics. The first person to kind of look at the duality of the electron was a guy named Werner Heisenberg. And he worked closely with Bohr. He was kind of an apprentice of Bohr. And he really liked the Bohr model, but thought that it really didn't do the electron justice. He thought that the electron had more wave-like characteristics than Bohr gave it credit for. And so he kind of, along with Bohr for a while, but he kind of split away from Bohr. He came up with these complicated mathematical equations that dealt with the probability and the location of where an electron would be. They dealt with a lot with math, a new math that he kind of invented, which was matrix mechanics, using equations and columns and rows to figure out some sort of mathematical answer about where the location and the velocity of an electron. So he published all these papers, and they were really, really complicated, and they were really well accepted. But then a guy that came along named Irvin Schrodinger, which I have his name right over here, Schrodinger, and he developed a simpler mathematical equation which dealt with wave functions, and he was able to come up with an equation to calculate the velocity and the position of an electron. So an electron, they thought, behaved like a wave, traveled in waves. He could know the velocity of that, how fast it was moving, and where exactly on the wave that electron was going to be. However, there were some flaws with that. As Heisenberg and Schrodinger pointed out. If I can find my cursor here, we'll go to the next slide. So the model of an atom not only looked like what Bohr thought the atom looked like, which was this atom with energy levels, energy level 1 here, energy level 2, energy level 3, but the electron did not travel in just circular patterns around those energy levels. It actually traveled in kind of wave-like patterns, like the dotted red lines suggest. So not really could we ever really know the exact location of electron. That's what these wave functions that Schrodinger and Heisenberg came up with. No one could really ever know the precise velocity and the precise position that an electron could be. However, you could know the probable location. So they came up with these things called probability maps. And we call those probability maps orbitals. So you can write down that orbitals are basically probability maps. I'll just put prob maps. Okay, so there are probable locations that an electron can be found. Okay, so here, these kind of little, these kind of balloon-shaped ones, those are all electron probability maps. So they came up with the whole theory, and the theory had 4 parts, basically. Had 4 quantum mechanical numbers. But the uncertainty principle, which Heisenberg came up with, said that if I can get this to right here. Oh, go back. Go back. Okay. It said that the precise location I'm having trouble with the mouse today. Oh, because the precise location of an electron could not be known. Only the probable location. If I could write. Okay, only the probable location. Okay, so the probable location could be determined by the use of what are called quantum numbers. So the principal quantum number is denoted by the small letter n, and it represents the energy level of the electrons. So the energy level of the electrons, those are just the same as the Bohr said. He said it could exist as 1, 2, 3, 4, dot, dot, up to how many electrons you got, how many energy levels you got. Okay, to find out how many electrons can go into those energy levels, they came up with the equation 2 times the value of n squared. So if I plug my n value in, for instance, if I plug 1 in for n there, I get the number 2. So 2 electrons can go, I'll just represent electrons by E minus. 2 electrons can go in that first one. You'll figure out that 8 can go in that next one. 18 can go in that third one. And then 32 can go in that next one. Okay, so that told you how many electrons could go in each energy level. Okay, now where were they going to go? So that's what the azimuthal quantum number, or L number, sometimes it's denoted by that L, that refers to the 3D shape of your orbital. Okay, so your orbital can be, remember we talked about these last year, they're S, P, D, and F. So the orbital refers to the shape of these. So the S ones, remember, are spherical shaped. The p orbitals are kind of like balloon shaped or dumbbell shaped like that. And then D's kind of like a mixture of both those. A mix. And then the F orbital is really complex. We'll just put complex. So the ones you need to know are the S orbitals and the p orbitals. And we're going to look at those right now. Okay, so the next quantum number describes the orientation of those orbitals. Okay, it's called the magnetic quantum number, and it's denoted as M sub L. So ML. And it shows you the orientation. So the s orbital really only has one orientation because it's circular, but the p orbital can be on the x-axis as it is here, on the y-axis as it is there, or oriented on the z-axis. Okay, so that can be positioned in 3 different ways, basically. So the s orbital has 1 position, and the p orbital has 3. Oh, that does not look like position at all. And you'll find out that the d is equal to 5 positions. Okay, we get there. So that just tells you the orientation. On the x, y, z axis, they get more complex as you start adding more of these spatial patterns, these orbital patterns that where electrons are. And then the last one is telling you that it's called the ms, or the magnetic spin number, the spin quantum number, and that tells you which way the electrons are spinning, clockwise or counterclockwise. Okay, so are they spinning clockwise or counterclockwise? Okay, that's an electron. Sometimes they're represented by up and down arrows. So they can either have a value of minus 1/2 or positive 1/2. All right, so those 4 quantum numbers all give you the precise location of where you can probably find an electron. Okay, they're not for sure going to be there, but that's the most probable location that you can find. And we're going to work out an example now of finding quantum numbers.